In business, we're all pretty obsessed with averages, right? Average sales, average delivery times, average performance. But here's the thing. The biggest risks, and sometimes the biggest opportunities, they don't live in the average. They hide in the variation. Today, we're going to unpack the F-test. It's an incredibly powerful tool that helps smart leaders look past the average to measure what really matters: consistency. It's all about managing risk and making decisions you can actually count on.
Okay, let's make this real with a classic business problem. Imagine you've got two suppliers. Supplier A gets you parts in 3 days on average, but sometimes it's 1 day and sometimes it's 5. Then there's supplier B. They average 4 days, but man, they hit that 4 day mark almost every single time. Now, supplier A's average looks better on a spreadsheet, but that inconsistency, that variance, that's a huge hidden risk. One late delivery from them could shut down your entire production line. So, you see, the real decision here isn't just about speed, it's about predictability.
So, to tackle this kind of problem, we need a solid game plan. Here's our roadmap for today. First, we'll really dig into this whole problem of variation and why it's so important. Then, we'll build out our toolkit with the F-test framework itself. After that, I'll walk you through the step-by-step process for actually doing the test. Then, the fun part, we'll apply it to some real-world case studies. And finally, we'll wrap up with the key takeaway that you can start using right away.
Okay, let's kick things off with part 1, really framing this problem of variation. Why isn't looking at the average good enough?
Well, think about it. You can build a reliable plan around a process that's consistent, but you can't plan around chaos. When a key part of your business is all over the place, it creates all these downstream headaches. We're talking missed deadlines, budget blowouts, and of course, unhappy customers. This is exactly why we need a statistical tool, something to tell us objectively if the difference in consistency between two options is a real meaningful signal or if it's just random noise.
And that brings us right to our solution, the F-test. Let's build out the framework. Seriously, think of this as the secret weapon in a consultant's toolkit for turning a gut feeling about inconsistency into a rock-solid data-backed decision.
At the heart of this framework is something called the F-distribution. You can just think of it as our master map. It's this theoretical landscape that shows us the probability of every possible outcome when you compare two variances. Once we understand this map, we can figure out if the result we got from our data is just a common, everyday thing, or if it's something genuinely statistically significant.
Now, this map isn't a one-size-fits-all kind of thing. Its exact shape actually changes based on your sample sizes, with the pros called degrees of freedom. Basically, the more data points you have, the more reliable your comparison is. So as your degrees of freedom go up, the shape of this curve tightens up, becoming less skewed and more focused, reflecting that you have more statistical power.
So if the F-distribution is our map, then the F-statistic is our "you are here" pin. It's the one specific value that we calculate from our own data. And the formula? It's beautifully simple. It's just the variance of one group divided by the variance of the other. That one number tells us exactly where we've landed on that big probability map. Now, it's really easy to get this mixed up with a t-test, so let's draw a super clear line in the sand. A t-test asks a question like, is machine A faster than machine B? It's about averages. But an F-test asks, is machine A more consistent than machine B? It's all about the variance. It helps us compare the stability of whole systems, not just single data points. All right, we've got our framework. We know the what. Now, let's jump into the how. This is the clean, repeatable process for actually putting the F-test to work.
It's a straightforward 6-step process. First, you state your hypotheses, what you assume is true versus what you're trying to prove. Second, you decide on your risk tolerance, your significance level. Third, you calculate your F-statistic. Fourth, you find the critical value. Now think of this as your line in the sand. It's the threshold you get from our F-distribution map. Fifth, you compare your F-statistic to that line. And finally, step 6, you make the call. If your number crossed the line, congratulations, you've found a significant result. Look, theory is great, but seeing this in action is where it all clicks. So let's put this framework to the test. We're going to walk through 3 different business scenarios to see how the F-test takes us from a pile of raw data to a clear, confident decision. Okay, case number 1. This is a classic "did we make things better" question. An agricultural tech company is testing a new fertilizer. They don't just want taller plants, they want more uniform plants.
Their hunch is that the old way was way more variable than the new way. Since they're only looking for an improvement in one direction, this is what we call a right-tailed test. And here's their data. The old process had a variance of 600. After 6 months with the new fertilizer, the variance dropped to 400. Now, on the surface, that looks like a clear improvement. But is that drop big enough to be statistically meaningful, or could it just be a fluke? So first things first, we set up our hypotheses. The null hypothesis is kind of the skeptic. It assumes there's no real improvement, that the new fertilizer is the same, or maybe even worse. The alternative hypothesis is what we're actually trying to prove, that the initial process was significantly more variable than the new one. Now we just run the numbers. We get our F statistic by dividing the larger variance, 600, by the smaller one, 400. That gives us 1.5. Then we look at our F distribution map to find that line in the sand, the critical value. For their sample sizes and a 5% risk level, that value is 4.88. And here's the moment of truth. Our calculated value of 1.5 doesn't even come close to crossing the threshold of 4.88. So the big insight here is that even though the variance looked like it decreased, the change just isn't big enough to be statistically significant. We have to conclude that we fail to reject the null hypothesis. We just don't have the proof to claim the new fertilizer really improves consistency. Let's move on to our next case. Here, a manufacturer needs to pick between two battery suppliers. They don't really care which one is better. They just need to know if there's any meaningful difference in their consistency. A big difference in either direction could be a problem. This kind of "is there any difference at all" question calls for a two-tailed test. So they test batteries from both. Supplier A has a variance of 36 hours. Supplier B has a variance of 28. Okay, so supplier B looks a little bit more consistent. But again, is that difference real or just random chance based on the samples they tested? We calculate our F statistic. 36 divided by 28 gives us 1.285. Now, because this is a two-tailed test, we actually have two lines in the sand. Our result has to be either unusually small, less than 0.389, or unusually large, greater than about 2.76, to be significant. Our calculated value of 1.285 lands right in that safe zone in the middle. So the conclusion? Again, we fail to reject the null hypothesis. There's just no statistical evidence here that one supplier is more consistent than the other. And that's actually super helpful. It means the manufacturer can now make their choice based on other things, like cost or service, and feel confident about it. All right, one final case. This time, we're looking at a very specific claim. An e-commerce company wants to prove that their delivery network in Boston is more consistent, meaning less variable, than their network in New York City. Because they're testing for a specific less than, this is a job for a left-tailed test. So they track deliveries. Boston had a variance of 38 hours, but New York City, a whopping variance of 83 hours. I mean, the raw data here is screaming that Boston is more predictable, but let's see if the stats back it up. Now, for a left-tailed test, we flip our calculation a bit. We put the variance we think is smaller, Boston's, on top. So 38 divided by 83 gives us an F statistic of about 0.458. For this to be a significant result, our number needs to be less than our critical value, which in this case is about 0.518. And there we have it. Our calculated value of 0.458 times is less than our critical value of 0.518. It crossed the line in the sand on the low end. This time, we can confidently reject the null hypothesis. The company has statistical proof to back up its claim. Their Boston delivery network is significantly more consistent. That's a huge win. So after all that, building the framework, running through the cases, what's the real bottom line? What's the big data-driven idea you should walk away with? Let's boil it down to 4 key things. First, the F-test is your go-to tool for comparing consistency. Second, it shifts your focus away from just looking at averages to the things that really drive your business, risk and predictability. Third, the math behind it is just a simple, intuitive ratio. And finally, when you follow this structured process, you can move from just having an opinion to having a clear, logical, and totally defensible conclusion. So, I'll leave you with this question. Where in your own work are you relying on an average that might be hiding a huge risk or a massive opportunity? What's one decision you could make tomorrow with way more confidence just by applying this simple test for consistency? That, right there, is the power of moving beyond the average.